Heating last call, I guess. This will be the sadly last session for the day, but it's fully packed with 4 slots this time. They're a little bit shorter, unfortunately, but that's why we'll go right ahead and have Dina talk about.
Okay. Hello everyone, my name is Dina Borrego, and today I will present you the work I have been developing with my supervisors that it's about maintaining invariants in local first systems. So, local first is a new programming paradigm that allows users to keep the ownership of their data by keeping their primary copy locally while using the cloud for collaboration, synchronization, and replication. The key ideas for local first are the ability to process data locally, possibly in an offline mode, as well as collaboration across multiple devices, improved security and privacy, and long-term data preservation. However, supporting collaboration in such a model poses consistency challenges when dealing with conflicting concurrent modifications and intermittent network connectivity. To ensure state convergence, we can use CRDTs. However, it's important to note that CRDTs alone may not be sufficient to guarantee a globally consistent state. Let me show you an example. In an album management system, we can define a foreign key constraint between albums and artists, ensuring that for every album in the database, that also exists the corresponding artist. Imagine we have 2 copies of the same data, one locally stored and the other in the cloud. Initially, both copies are synchronized and they both contain an artist. Now, let's say that we insert an album into the local copy, while at the same time another user deletes the artist from the database, updating the cloud copy. At this point, both copies are correct, and they both reflect their respective operations. However, after propagation, we end up in a state where referential integrity is compromised. Thus, besides convergence, we also need to guarantee the maintenance of the invariants, and for that, we need mechanisms. However, not all mechanisms are well suited for local first systems. For example, if we attempt to use locks on conflicting operations, we will lose the ability to work offline because replicas would need to synchronize to obtain the lock. Therefore, our goal is to have non-blocking mechanisms to enforce the invariants and verify their correctness with a mechanical way. Antidote SQL is a database system that combines strong and weak consistency and that uses a non-blocking conflicting mechanism to handle referential integrity. As this mechanism does not use synchronization, we can apply it directly to the local first setting. So I will quickly explain it to you. The mechanism uses an additional column where flags are placed according to the operations that are executed. For instance, when you see an I there, it means that the most recent operation on that record was either an insertion or an update. Now let's look at how this works in practice with operations. When an album insertion occurs, we put a T in the visibility column of the artist's of the corresponding artist, and this tells us that this particular row has been touched, meaning that we have inserted an album that referenced that artist. The touch allows us to identify conflicts afterwards and handle them according to our predefined policy, that in this case is the Edwin's policy, so both the album and the artist would be retained in the database. As I mentioned earlier, one of our goals is to verify that the mechanisms work correctly and we indeed maintain the invariants. To do that, we followed the following methodology. So we start by providing the conflict resolution mechanism and the invariants that must be enforced by the mechanism to an analysis tool such as Z3, VeriFx, or TLA Plus and TLC model checker that verifies if the mechanism is correct. And this verification leads to one of three results. Aborted, in the case the tool times out. And in these situations, we need to simplify the specification. This is probably the most annoying case scenario because we don't have any hint about what to do to solve this problem. Wrong, if the mechanism is unable to maintain the invariants. And in this case, the tool is our friend, and it also provides us a counterexample to help understand what is the problem. After understanding the problem, we can correct it and verify it again. This is an iterative process that ends when the analysis tool returns a correct. And now we can celebrate because we are sure that the mechanism is correct. To prove the referential integrity mechanism, we opted for VeriFx, that is a high-level programming language that allows to develop RDTs and define safety properties that are automatically verified. And we started by implementing the mechanism and define the proof we wanted to demonstrate. In this case, the proof encodes the following. For any two reachable states that are also compatible and where referential integrity holds, if we merge those two states, we get a new state where referential integrity still holds. However, this proof is quite heavy because it has multiple loops, which resulted in an abortion by Z3. To access the effectiveness of the mechanism, we then create tests in VeriFx based on the earlier example. The tests allowed us to verify that for those specific examples, the invariant is maintained. However, this is not ideal, and we are working on the simplification of the previous proof to get it correct. At this point, we had a mechanism that we knew worked for referential integrity, so the idea was to generalize the approach for other types of invariants. And if we look closer to the referential integrity formula, we see that this part here can be expressed as an implication. So, referential integrity can be seen as a specialized form of an implication, and an implication is a disjunction which leads to the question, why not extend the touching mechanism to handle implications and disjunctions? And that's precisely the direction we have been exploring since then. When dealing with a disjunction, as illustrated in this example, the underlying concept remains the same. However, rather than having the visibility column associated with each row, we have the visibility column associated with each column. Another difference between referential integrity and disjunctions is that in referential integrity, we know which operation must execute the touch, while in disjunctions is not straightforward. In this specific example, we have chosen an operation to execute the touch, but we are exploring some other solutions. Now let's delve into how this works. Suppose we have designated the operation that updates the nationality as the one that executes the touch. So when the operation is executed, a touch is affixed to the naturality column, and the operation that updates the naturality does not change and proceeds in the usual manner. After propagating the operations, due to the presence of a touch on the naturality column, the operation that updated the naturality would have no impact. To validate the correct functioning of the touching mechanism for disjunctions, we specified it in TLA+, and we subjected it to verification. We performed this verification across 4 different models, each distinct in the terms of the number of replicas that we consider and the number of predicates involved in the disjunction. And for all the models, we were able to verify that the specification was correct. Before concluding, I just want to emphasize that local-first applications require convergence and preservation of the invariants. In our work, we verified a referential integrity mechanism, and we saw that this mechanism can be directly applied to a local-first setting. Currently, we are trying to generalize this mechanism for other types of invariants, such as disjunctions. Thanks.
First question already?
Thanks for the great talk on this important problem. I'm curious, how application-specific do you think these kinds of invariants are? Do you envision individual application developers going through this kind of process, or are you imagining more, CRDT developers using these techniques to develop more general invariants?
Okay, in the slide that I showed with the verification process was designed thinking on the person who is designing the mechanism. But the idea that we present on the paper is actually a little bit different, and it's an automate. Basically, it was for programmers, and the programmer would provide the specification of the database as well as the invariants and the mechanisms to enforce those invariants, and the whole application would be verified against those mechanisms.
So one thing I was wondering about is, so you started focusing on referential integrity, which is very much from databases. So was this driven by prior work on database-like systems, or did you think about a concrete set of applications that you wanted to support? If so, can you elaborate on that one?
Okay, so I am not working specifically in the local first setting. So when I thought about using the mechanism for referential integrity in these junctions, the idea was more general than that. But when we submitted to PLF, we saw that this can be also applied to the local first setting, because we don't need any logs to do that.
Certainly, but I was a bit wondering if, I'm always looking for what people, what mental model people have of the world, right? What motivates you to select a certain type of application, you and your research group, I guess. It's not just about you personally.
Okay, so how do I choose the examples that I use?
Maybe.
Okay, so referential integrity is a well-known invariant in databases.
So you choose that because it's like a standard thing.
Yeah.
Not for a particular application.
Yeah.
That was basically my question.
Hi, great talk. I saw that you use 5 to 10 operations to verify your model. Did you try more operations? If so, how was the result?
I don't think I understood your question, sorry.
Can you switch to the slide that you are this slide. Just back. No, next one. Yes, you use 5 or 10 operations to verify your model. Did you try more operations, and was it converged or any other result?
Okay, here the number of operation does not represent, I can have a lot, for example, in this situation, we have the update nationality and the update naturality. If we model this example in TLA+, when we check it in TLC, what happens is that it generates models where 10 operations are executed, and it tests it explores all the space, so with 10 operations executed. But it can be different operations. The type of operation that is executed don't matter.
Okay, I was just wondering if there are edge cases not be covered by 10 or 5 operations.
Yes, it can happen, but if we don't restrain the number of operations, the model is too heavy to be proved. And that's why we need a threshold on the number of operations that are executed.
Okay, thanks.
Triggered by that question, a question to everyone in this room. Is anyone using not model checking, but proving things with Acta or Isabel in this space?
Yes.
You can look forward to the last one.
Okay, I will very much.
One more, if we have time, briefly. So the idea of maintaining an invariant, in your case, for example, the foreign key integrity, you can maintain the invariant by pretending that a certain operation never happened, like, for example, the deletion of the entity that is being referenced, and drawing a link maybe to the earlier talk on move operations that also had the same idea of maintaining the invariant that there are no cycles by also pretending that a certain operation never happened. I'm just wondering, do you think that's like a general pattern that to maintain invariants, the right approach is just to exclude certain operations from the history, or I'm wondering if that's like a larger pattern that we should be thinking about here?
Yeah, I think that, yeah.
I don't really know where the thought is going. I just wanted to throw it out there.
Yeah, so maybe just a comment about what you just said. I mean, if you don't delete, then you would have to do some transformation, and that sounds a lot like OT rather than, yeah. So maybe delete would be the most in line with the CRDT approach, I guess.
I see it more as adding a compensation than really adding what happened in the past. So, because someone really tried to add modified one of the values, right? So it's not like you're adding in the history, just someone preemptively tried to prevent the conflict by executing an extra operation. So I think you can see it as adding the history or doing a compensation to prevent the conflict proactively.
One thing I hear from users actually often of CRDTs is that they want transactions. And specifically, it feels really adjacent to this work in the sense that what they mean when they say they want transactions is that they want to see either all or none of a particular operation group, right? And so if there's a conflict on one part of the key, they want all the rest of that collection of work to be somehow rejected, which I don't know what that means for a CRDT. Like everything is sort of thought about at a register level, like under the hood. So I'm wondering actually whether this work can be also taken in a direction where, if you can detect these invariants are being invalidated, you could have an invariant that says, oh, there's no conflicts on any keys in this group of operations, and if there are, we'll ignore the whole set. So I feel like maybe there's an interesting opportunity there to like solve a problem we've had for a while, but I don't really know how you would get there from here. But people want it. I get asked, I don't know, once a month or so.
Did you ever look at the delta state, Aaron?
Yes, I've asked that for those on the stream. He asked if I looked at the delta state. I can.
Not to bring up our database-backed CRDT like yet again today, but part of the rationale behind that approach, where we essentially write all of the CRDT updates into a database, and then we run database queries over it, is that we can then borrow all of this kind of thing, right? So we were doing atomics and transactions and all this stuff in CRDTs to say like all or none of these operations, right? And as this presentation was going on, I was like, we could, if we ever pick that project up again, I would totally use this. So.
So I would argue that both, like some of the problems that you're talking about here, and the problem, like the idea of having transactions in CRDTs. Another way of framing it is that people have CRDTs with their own semantics. You know, where they have operations that don't correspond to just changing a register, right? So if you need a transaction, probably, you know, it's like, you know, the prototypical transaction is I need to move money from this account into this account. So you can have an operation that is move, and it specifies an amount in a from account and a to account, and it's just one operation, and the operation, you know, stays or goes. And a lot of the, I'm not sure about the referential integrity thing. I hadn't really thought about that, but a lot of situations where you're worried that different operations might result in you know, violating these invariants, what you actually need then are your own custom semantics inside your CRDT, and your own detection of what conflicts are, your own definitions of what a conflict is, and your own rules for how you resolve those conflicts.
If there are no more pressing questions, I think we can also go on to the next speaker, to be honest. And thank you very much again.
Thank you.